Okay, so this is the analysis of the electrocardiogram presentation. So when defining a normal EKG, you need to remember that the exact wave configuration can vary from one lead to another, but they should be normal in sequence. Once again, defining a normal EKG, you need to remember the exact wave configuration may vary from one lead to another, but they should be normal in sequence. In other words, the P, Q, R, S, and T should always be in that sequence. So that's the big thing to remember. When we're looking at the EKG paper, it consists of a series of horizontal and vertical axes. The horizontal line indicates time. The vertical axis indicates voltage or the strength of the current. So voltage or the strength of the current. So when we're looking at EKG paper, one of the first things we're looking at is the distance between each of the small vertical lines, or one small square, which represents 0.04 or 400ths of a second. So each distance is 0.04 hundredths of a second between each of the small vertical lines, or one small square. The distance between each heavy vertical lines, or one large square, represents 0.20 or 0.2 hundredths of a second. Each large square on the paper, which is what you see over here, will consist of 5 small squares. That's where 0.04 comes in 5 times, which would be 0.20. So 5 large squares equals 1 second on an EKG paper. So since each large square equals 20 hundredths of a second, it takes 5 of the large squares to do 1 second. So this is when you can actually look at what a heart rate is off of an EKG, and most EKG machines will look at this for you, but you should be prepared to look at strips and tell me what the heart rate is off of an EKG strip. So when we're looking at the EKG paper, 1 minute equals 300 large squares. 5 large squares per second times 60 seconds equals 300 large squares per minute. So 1 minute is 1,500 small squares. So if we have someone that has an irregular rhythm, we can't just count from R to R wave. To calculate the heart rate, we actually have to look at, over the course of a minute, what was their heart rate. So you have to count the R waves in 1,500 small squares, or 300 large squares. So the electrical activity generally proceeds through heart through an orderly sequence. The normal EKG for one cardiac cycle consists of a series of positive and negative waves. So the positives go above the line, negatives go below the line. These are called the P, Q, R, S, and T waves. Positive and negative waves. The P, Q, R, S, T waves represent various phases of the cardiac repolarization and depolarizations. Remember, wave configuration is different in different leads, but they should all come in the same sequence as P, Q, R, S, and then a T wave. So you should still have that order of P, Q, R, S, and T waves, but the way the leads are in the 12 lead EKG, or 12 different views of the electrical activity, they may look different in each lead, but they should still be in the same sequence of Q, R, S, and T. The isoelectric line is the point of departure for the P, Q, R, S, and T waves. It's also called the baseline or isoelectric line. So that's that baseline. This is the point of departure. This is the point of, okay, we're going to leave from this location. Waveforms. A single waveform begins and ends at baseline. So this would be, it begins at the isoelectric line, it ends at the isoelectric line, right? It begins and ends at a baseline. So waveform begins and ends at a baseline. Two or more waveforms together, by definition, is called a complex. I would remember this. The QRS sequence is called a complex because there are two or more waveforms together. The P wave is not a complex because it is one waveform. The T wave is one waveform. Therefore, it is those two, the P and the T, are not considered a complex, but the QRS is considered a complex because it is two or more waves together. A segment is a flat or straight or isoelectric line is what we're looking at here. So the ST segment is going to be the more important segments to us, and we're going to talk about that more, but that ST segment is where we can look at a lot of myocardial injury, especially when we look at what's called a STEMI. So a ST myocardial infarction is called a STEMI, S-T-E-M-I. So we'll get more into that, but the ST segment is going to be the big one. So we'll get more into that here in a second. The intervals. An interval is a waveform or a complex connected to a segment. So it's the analysis all together. The PR interval is something that we'll look at for certain things. The QT interval is something that we'll look at for certain things. So it's connected to a segment. So if we look at the PR interval, you see the distance between the P wave and the R wave. That's what we're looking at. We're connecting a waveform or a complex to a segment. Well, the segment is that point or flat time in there. So how long it took to get from the P wave to the R wave if we're looking at the PR interval. So that's how long. That's a good example of an interval, would be the PR or the QT. The P wave, this is the first wave of a normal EKG. This is also when someone has atrial fibrillation or atrial flutter. This is what can be abnormal in those cardiac arrhythmias. So the first wave of a normal EKG is the P wave. It is produced by depolarization of the right and left atrium. When the P wave is seen as a fairly smooth contoured positive wave in leads 1, 2, and 3, the electrical impulse is said to come from the SA node, which is the primary pacemaker of the heart. So if it's smooth and contoured and it is a positive wave in the 1, 2, and 3 leads, then it's from the SA. In other words, it originates from the SA node, which is the primary pacemaker. So this is good. That means you're running off the primary pacemaker. More about the P wave. At the end of the P wave, atrial depolarization is probably complete. The impulse then enters the AV node. Remember, we go from the SA to the AV node. There is no external wave produced as the impulse travels through the AV node. So we see the SA, and then there's no electrical activity, so that's the isoelectric line. As it goes through the AV node to the ventricular conduction system, it does not show an impulse on the EKG. The QRS complex is produced by depolarization of the left and right ventricles. So that represents electrical activity going through the ventricles. So if we see a really wide QRS complex, that means the ventricles or the electrical activity going to the ventricles is very, very sick or disrupted. That can be a sign of cardiac disease. Initial negative wave of the QRS complex is called the Q wave. Remember, that's that first wave that goes down, as you can see in the PowerPoint. The Q wave is characteristically seen in some, but not all, the leads of the EKG. In other words, you might not see it in some of the 12 leads, you might see it in some. When it's significant is when it's like a half to a third of the distance of the QRS of the R wave. That's when we really get concerned, but that will be something you'll cover in a different course down the road. So Q wave can be significant, but not something I want you guys to worry about quite. The QRS complex. The first positive wave of the QRS complex is the R wave, and R does not have to be preceded by a Q wave. In other words, we can go P, R, S, and T, right? We don't have to see a Q wave in every single lead. It does not have to be preceded by a Q wave, and R does not have to be preceded by a the QRS complex, when we finish with the R wave, a negative wave extending below the baseline after the R wave in the QRS complex is called the S wave, right? That's the last one that comes in there in that complex. That S wave is a negative or below the baseline wave. So when we're looking at the QRS complex, we may assume many different configurations depending which lead that you're looking at. Extra waves are occasionally seen here and there, while some waves are not seen at all, like we talked about with the Q wave before. So no Q wave, sometimes the Q and the S are there, but you don't get a clear R wave, or there might be an extra wave depending on what's going on with the patient's cardiac activity. So regardless of configuration, it is still called the QRS complex. So even if you don't see the Q, like you see in this QRS complex example, it is still called the QRS complex, even though the Q is missing. They are a group of trio, so even if they break up, they are still referred to as the T wave. Usually the T wave of an EKG, usually the final wave of a normal EKG wave is the T wave. So this represents repolarization of the ventricles. So repolarization of the ventricles would be a T wave. Depolarization would be the Q complex. The atria do repolarize as well, but the atrial repolarization is generally not recognizable on an EKG. So in other words, you won't see the atria repolarize. They won't give a waveform of repolarization, but you will see a ventricle repolarization, which would be the T wave. Because of the low voltage, or because it's buried in the QRS complex, you will not see the repolarization of the atria, but you will hopefully see a repolarization of the ventricles. The U wave, occasionally a U wave is seen after a T wave. The U wave is of no significance in the analysis of cardiac arrhythmias. So the U wave, and I think I have an example on this next slide here, is of no significance to the analysis of arrhythmias. Here's the example of a U wave. So there's a T wave where you have the ventricular repolarization. There's that negative U wave, and then you're back to baseline, and then you follow with a P, Q, R, S, T again. So no significance, not something we usually pay attention to for most cardiac cases. Time intervals, this is where we get into the first ones. The first one that we'll talk about are the great importance ones. And so the PR is going to be a big one, and that's why I mentioned it earlier. This has a wave and a segment, so therefore it is considered an interval. So this is the interval from the beginning of the P wave to the beginning of the Q wave. From the P to the Q wave. From the P to the Q. So this has a wave and a segment, and therefore it is an interval. And this represents atrial depolarization plus the time needed for the impulse to travel through the AV node and the ventricular conduction system. So the time needed to travel through the AV node and the ventricular conduction. The P wave is atrial depolarization. Atrial depolarization. The remainder of the PR interval is created by the impulse traveling through the AV node to the ventricular muscle. So if there's damage or injury, then that's going to delay and cause a PR interval. So because it's important we know what the PR interval is, we need to look at what a normal is. So 10 hundredths of 20 hundredths of a second is the normal. So this would be 3 to 5 small squares. So there should be normally 3 to 5 small squares for the PR interval. So if you want to see what a normal is, we're looking at 3 to 5 small squares between the P and the R interval. So conduction here is being delayed in the AV node if it's greater than 0.20. Greater than 0.20. So what does that mean? Something is slowing conduction from the AV node to the rest of the heart. This could be something like a heart block, right? So this is something that we're going to look at when we start looking at heart blocks, is that P is it greater than 0.20, then that could be a sign of a heart block. So that means the electrical activity is slowed down, something is wrong. Just like if you hurt your knee, you're going to slow down because something is wrong. Same thing here. The longer the PR interval, the more likely there is something that's wrong with it. From the onset of the first wave of the QRS complex to the termination of the QRS complex is the QRS complex interval. So how long this complex takes to occur. A normal is 4 hundredths to 12 hundredths. I know it says 0.9 seconds. I remember this. Normal is 4 hundredths to 12 hundredths of a second. I know what that picture said, but a normal is 4 hundredths to 12 hundredths of a second. So it should be no more than 3 small squares, or it should be less than 0.12 seconds. So same thing, no more than 3 small squares or less than 0.12 seconds. If it's long, if it's prolonged, which means it's a wide QRS complex, so this is beyond 12 hundredths of a second, the conduction through the ventricles is abnormal, which is bad because QRS complex represents ventricular conduction, or hopefully contraction is what we're ultimately trying to get through here. So if that conduction is abnormal, if it takes a long time, then that means the ventricles aren't working and you're about to be in a very serious situation with this patient. So occasionally, the measurement of the QRS complex is difficult to measure. The final wave may not return to baseline, so the exact point at which the QRS complex ends sometimes is not clear, and therefore it makes it pretty hard to determine what the exact time interval is for the QRS interval. The interval will appear thinner than the rest of the other waves since it usually happens rapidly. So this is a very fast, rapid sequence. One method of determining the end of the QRS interval may be to see where the line gets thicker again. So that's what you see over here on the picture, is you see that rapid QRS complex and then you see it get thicker. Well, that's where we could say that's where the QRS complex ended and we're going back again. So that is one method that's out there. The QT interval is from the beginning of the QRS complex to the end of the T wave, right? That's the QT interval. And it may be shortened or prolonged with various cardiac problems. So this is where you can look at the electrolyte imbalances. So if you have low potassium, or you have a severe electrolyte problem, this is where your QT interval can be affected. So we see these people with hypokalemia, hyponatremia, so on and so forth. All these electrolyte imbalances, whether they're hyper or hypo, can cause either a shortened or prolonged QT interval. So if there's a QT interval that's abnormal, one of the things that should be evaluated is the electrolyte status. The ST segment. This is one of the most important ones to pay attention to, especially working in acute care medicine. If that's your goal, from the end of the QRS complex to the beginning of the T wave is the ST segment. A normal time for the ST segment is less than 0.12 seconds. less than 0.12 seconds. This may be elevated or depressed in relation to the baseline. In the presence of some mild myocardial anomalies or injuries. So if it's depressed, if it's lower than baseline, or if it's higher than baseline, that could be a sign of ischemia or injury ultimately. So it's a sign of very, very things, right? So this is what you'll see with the ST segment that goes back to baseline. The next one that you see here in the middle, the ST segment is elevated, so that would be a ST MI, right? It's ST elevated myocardial infarction. Elevation is myocardial injury or ischemia. Depression usually means ischemia. It's been going on for a long time. So some people might have just a normal baseline where it goes below because they have a history of an MI. So things that you need to be aware of if that's their normal. Obviously, we're going to get their troponin values as well. So it's pretty important to look at that ST segments. Right, so the big thing you need to be able to do is to draw PQRS complex and T complex, PQRS, T waves, and then be able to sort of figure out what's going on with the cardiac cycle during this process, right? You should know your normal segments. You should know the normal time intervals for all of these. Interpreting an EKG is a 5-step approach. You look at the heart rate, the rhythm, how regular the rhythm is. So if it's regular, that means every 5 boxes there's an R wave, so on and so forth. That would be regular. Or it could be 5 boxes, 3 boxes, 2 boxes, 5 boxes. That would be an irregular rhythm, right? So we're going to look at the P wave. Is it there? Is the PR interval normal? Is the QRX complex narrow or wide? So we're going to look at all of these things. I do expect you to be able to calculate a heart rate from an EKG strip. That's required. That is not a mandate of me. That's a mandate of the curriculum. So it's pretty easily determined ultimately. So even on the board exams, they'll give you an EKG strip, and then it's part of a whole scenario question and ask you ultimately what's going on with this patient. You should know if it's a Brady, TAC, something like that, right? So the most appropriate method is that an irregular versus irregular will all determine how to calculate it. I know you guys love calculations, so here we go. If it's a regular rhythm, it makes it pretty easy. You count the number of large squares between 2 consecutive P waves and divide this number into 300, right? The result will be the atrial rate. If we're looking at the P waves and the distance between 2 consecutive P waves, that tells us our atrial rate. So here you see the example. We have 4 boxes in between P waves, so that means our ventricular rate or atrial rate is 75. I know it says ventricular rate, but our atrial rate is 75. Atrial and ventricular rate should be determined separately because sometimes a P wave and a QRS complex may not listen to each other and they might do their own things, especially if there's a heart block. So that's why we need to separate them out. So I might ask you what's their atrial rate or what's their ventricular rate. So should be determined separately. Sometimes they don't always correlate with each other. So we'll look at some arrhythmias where they won't be the same, and that's why you need to here. So regular rhythms, this is a different method to look at regular rhythms. You can count the number of small squares between P waves, and this is what, and between consecutive R waves. This number is then divided by 1500. Oh heavens. Oh, so this is the ventricular rate one, right? So this is the ventricular rate where you'll look at the same thing divided by 300 to get the ventricular rate, just like we seen in the previous one. Sorry, I was looking at the different method, the 15. So this is the different method. So instead of dividing by 300, you could divide by 1500. So you can count the small squares and do it by 1500. The choice is yours if you want to do large squares or small squares. It's which division you want to do, 300 or 1500. As long as you remember which one goes with which, either method is considered correct. So this is where we divide it into 1500 instead of 300, so you can count small squares if your eyesight's good enough for such things, or you can do large squares divided by 300. Irregular rhythms, we cannot do this, so this is where we want to obtain a 6-second strip, and this is where we'll look at a ventricular rate. So for 6-second strip, we'll count the number of R waves and multiply it by 10. So just add a 0 behind it. So if I count R waves, if I count 10 R waves, then their heart rate is 100, right? Because I took their 10 R waves and then added a 0 to it, which is what happens when you multiply something by 10. And now their ventricular rate is 100, which is still within limits. So if it's irregular, then you cannot count the boxes. If it's irregular, you cannot count the boxes. You need a 6-second strip. Irregular rhythms, if you want to count the atrial rate, you have to have definite P waves that are not present in this strip. So if you cannot, or count the P waves and multiply it by 10. So you need to look at the P waves in a 6-second strip and multiply by 10. So you cannot count the boxes in between P waves in an irregular rhythm. If it's regular, use the box method, divide by 300. If it's irregular, you cannot do the box in between. You have to get a 6-second strip, count the number of P waves, and multiply it by 10. So how do we determine if the rhythm is regular? So the big thing that we're going to have to look at when we start counting is this R to R interval. Two other R to R intervals. Do we have the same number of boxes between the R waves consistently? If these R intervals, R to R intervals, vary, then it is an irregular rhythm. It is not regular if we do not have consistency between R waves. So if all of the R to R intervals are equal, the rhythm is said to be regular. In other words, every R to R has 5 boxes. The next R to R has 5 boxes. The next segment, R to R segment, is 5 boxes, right? So then that would be considered regular. If the R to R are not all the same length, then the rhythm is said to be irregular. So that's one thing you're going to look at determining the regularity is the R to R. So with slow to moderate heart rate, occasional variation of 4/100ths of a second of the R intervals is not abnormal. So if there's 4/100ths of a second in between the R's, between R to R in one area and R to R in another area, then that's within normal limits. That's just a normal variation. It's not considered irregular yet. Absolute equality of all R to R intervals would make the rhythm absolutely regular. Hey, you count 5 boxes in between this one, you count 5 boxes between this one, you count 5 boxes between that one. They're all that. They would be absolutely regular. So in other words, you could just count the boxes in between, divide by 300, or you can count small boxes, divide by 15. There you go. But if it's irregular, then you would have to get a 6-second, count the number of waveforms, and add a 0 or multiply by 10 ultimately. So irregular rhythms may be totally irregular or follow a pattern of variations. I know, isn't this great? They might be totally irregular or a pattern shows up. So we need to analyze or use a visual survey of the entire strip. So we need to analyze or use a visual survey of the entire strip. Once again, we need to analyze or do a visual survey of the entire strip. We can't just look at one PQRST and then call it good and move on to the next thing on that patient. We need to look at the whole strip and see if there's any abnormality otherwise. So we need to inspect the EKG strip for the presence or absence of regular occurring PQRST complexes throughout the strip. So we might have a P wave here, P wave here, P wave here, no P wave. We might have a PQRS, PQRS, P, no QRS, right? So that's what we need to look at overall. We can't just look at one tiny little snapshot of a PQRST and assume the patient's okay. We need to analyze the entire strip, make sure nothing like that is present. So when we're examining the P wave, we should answer three basic questions. First, is it present or absent? Is the P wave there? Good. Is there a QRS that follows? Good, right? So is the P wave present or is the P wave absent? The P wave's not there. That's not always a good sign. It might be visible in some instances, but not at other instances, especially when we start different arrhythmias. So is it present or absent? The second, we'll be looking at the shape of the P waves. Is it normal or abnormal? Is it a sort of a sawtooth pattern like you see in the abnormal shapes here, where it looks like the little teeth of a saw or a serrated knife, right? So that's what we're looking at there. Is it depressed? Is it sort of a spike compared to a round contoured shape? Is it present, absent? What's the shape look like after that? Normal P wave should appear as small and smooth, like what we see in the normal shape there. So this is your chance to really judge something by its appearance and be okay. The small and smooth contouring of the P wave should be indicative of the sinus pacemaker. It should be indicative that it's coming from that SA node. When we see abnormal or absent P waves, we might have a different situation going on. The P waves that differ from the normal configuration may be sawtooth, peaked, or inverted, aka upside down, otherwise different from the regular P waves. This would generally indicate that a site other than the sinus node may be in command as the pacemaker. So in other words, we might have an ectopic site, something that's exciting the ventricular contraction that's not coming from the SA node. In other words, it's getting its influence, the cardiac conduction is getting its influence from something other than the SA node, like in the case of a supraventricular tachycardia. It's getting its conduction for something supra or outside of that normal SA node. The third is each P wave should be followed or correlated to a QRS complex. In some cardiac arrhythmias, the QRS complex do not follow every P wave in a consistent relationship. So in some arrhythmias, we're going to see an instance where QRSs, they'll find their own way and do their own complex, sort of separate from the P wave. And this is something that we need. What's their relationship to the QRS complex? Because normally they should have good communication to each other. If they don't have good communication to each other, that can mean very, very bad things for that relationship. So if the P waves are present, then the PR interval can be measured. If the P waves are not, then you cannot. So if the P waves are present, then you can measure the PR interval. That's one thing that we want to look at. So if we want to measure the PR interval, we count the number of small squares included from the beginning of the P wave to the beginning of the Q wave and multiply this number by 400, so 0.04, and that's what you see over here in the box in the graph. PR interval is the number of small squares times 0.04. So this will tell us how long that PR interval is. So in this example, our PR interval is 0.16 because we took 4 of these small boxes or small squares times 0.04, which means we're at 0.1. So then we need to be cognizant of, is this normal? Is this high? Prolonged if it's beyond 0.20 or 5 small squares. So in the previous slide, we were at 0.16, so that would be a normal PR interval. If it was longer than 0.20 or 5 small squares, this would be a sign of possibly a first-degree heart block or hypokalemia. Those would be some of the things that we'd worry about if we had a prolonged PR interval. So big things just to remember here would be ultimately a first-degree heart block or hypokalemia. To measure the QRS interval, examine the QRS to determine whether the conduction of the impulse through the ventricles is normal. So this looks at ventricular strength and contraction. So how strong is that conduction ultimately? We're going to count the number of small squares from the beginning to the end of the QRS complex and multiply this number by 0.04 hundredths. So 0.04 would be what you're multiplying this. So number of small squares times 0.04. So if we have 2 small squares like you see in the graph there, we're going to multiply that by 0.04, which means we're 0.08. And so then you need to remember, well, what's a normal for this interval? Well, normal should not be any longer. It should not be any longer than 12 hundredths of a second. So 0.08 is perfectly within range. So please remember your normal ranges, especially when you're going to this test. So if the QRS interval is prolonged longer than 12 hundredths of a second, there is a defect of an impulse through the ventricles. There's a defect of impulse through the ventricles, like something's blocking the electrical activity through the ventricles, like dead tissue, for example, from a cardiac injury. Be sure to note whether the shapes of the QRS complexes within the strip are the same in between. So that's something that you can look at. We're looking at how similar they ultimately are to each other.